Today's lecture ECD. In last lecture, we started studying about the class C amplifier, and we solved a basic problem, and we studied expressions to compute the average power and the DC power. The DC power and the average power, PD average, for a class C amplifier. So in this lecture, we'll study about the tuned operation. This circuit is a bit different from the circuit that we studied in our last lecture, ECD28. What's the difference? It is the difference. Instead of having RC, now we have a tuned tank. Now we have a tank circuit, an LC, a parallel LC circuit. So why is this circuit there, and what is the advantage of having this LC circuit instead of a single RC? The remaining circuit, of course, is the same. We studied in last lecture that IC is in the form of pulses because this voltage is minus VB applied to the base with an RB resistor RB. So, and the output voltage was in the form of pulses, very small VCC, and then as the current flows, it goes down and reaches to a level minus VCE, reach to a level equal to VCE, the smaller voltage. So it was like this, right? VCC, and then it would go down to minus, and then it would raise up. So in fact, it won't go to a negative value. It was like this. It started at a value equal to VCC, and then it went down to a value equal to minus equal to a plus VCE voltage, and then it would be again VCC. So the output voltage was like this. It wasn't a sinusoidal wave. So now we are trying to have a sinusoidal wave at the output V out. So how can we have this V out equal to a sinusoidal wave? For this tank circuit, this parallel LC circuit will help us. Let's see how. The operation is described in A, B, C, D, and E, 5 steps. In 5 steps. These 5 steps are simple. In the first step, this capacitor is charged at a voltage VCC, C is charged, and the current is counterclockwise in this direction. So it charges capacitor. In the second step, this charged capacitor, once charged, it discharges itself when the input voltage is 0 once again. When the input voltage is 0, because but then when the input current is 0, when the input current is 0 once again at this point, the capacitor is not being charged. In fact, it will find a path to discharge itself. It will discharge itself through this inductor, and we have a clockwise current, and the output voltage will rise. Right, so it will rise to 0. It's negative, and it will rise to 0 then. And then in the third step, the inductor is charged, and now it will discharge itself and will charge capacitor. The direction of current remains the same, and the output voltage will rise to a value around VCC. And in the second last part, now the capacitor is charged, but in opposite polarity, it will discharge itself through inductor, and the current will be counterclockwise. The output voltage will go down like this. And the last step, this inductor charged in this way, it charges capacitor, and the current is again counterclockwise. So in these 5 steps numbered from A to E, the sinusoidal wave that we get at the output is like this. It started from minus C, goes to plus VCC, started from minus VCC, goes to plus VCC, and again comes back to plus VCC. And then if there is no continuous supply of the current pulses, the output voltage would go down and would finally be equal to 0. But thanks God, there is a continuous supply of current. Which one? This one. So the full cycle completes 0, and then once again we have this current pulse, and the whole operation starts once again. So as long as this pulse is there, the output voltage maintains its positive and negative peaks at plus VCC and minus VCC. So this is by virtue of these continuous pulses. Otherwise, the output voltage produced by this tank circuit would go down will die down and will become equal to 0 like this. So with by virtue of these current pulses, this voltage is maintained at the output, but they don't actually die because of these current pulses, thanks God, because of IC pulses. So the output voltage won't die. If these pulses won't be there, it would finally die to 0. So there is one purpose of this tank circuit. There is one other purpose. This tank circuit can be a frequency multiplier, because tank circuit, for a tank circuit, the resonance, this R stands for resonance. The resonance frequency is the frequency for which the XC is equal to XL. So it's a resonance frequency. So at resonance frequency XC, the capacitive inductance is equal to the capacitive reactance is equal to inductive reactance. The formula is this. So FR, if FR is equal to Fin, if we set FR is equal to the input, the frequency of the input voltage. What is the frequency of the input voltage? Let's go back and check this one. The frequency of this source. If the resonance frequency of this tank circuit is equal to the frequency of this applied signal, we have this output the same as we have drawn earlier. This output having the same frequency, the output has the same frequency as input, but it can be a frequency multiplier. If we set FR is equal to 2 times Fin, the frequency of the output signal, this is V out. This is V out. The frequency of the output signal is doubled compared to the input signal, the frequency of the input signal. So the output signal can have, with the help of this tank circuit, by adjusting R and C, we can have an output voltage that can be, whose frequency is the integer multiple or multiple of the frequency of the input source. So this is another application of having, or another use of having a tank circuit at the output. So that's all for this lecture. In the next lecture onwards, we will keep on studying more about Class C amplifiers. Thank you.